Hello everybody, we are early stage researchers from the Astro-Chemical Origins project, which is funded by the Marie Curie European program. We work on astrochemistry. Have you ever heard about it? If you are curious or if you want to know more, follow us in this astrochemical trip.
Within our galaxy, we find countless solar systems. Some are a lot like ours, while others are so alien that we struggle to understand how they came to be this way. The one thing they all have in common, though, is how they were birthed. Today, we will explore some of the physical models that have been produced to study the origins of stars and planetary systems. During this journey, we will visit different areas of the system and explore some of their characteristics. Here is the central object, the young protostar. This is the embryo of what will eventually become a star for this entire system. In this time, there are many physical processes that take place within it, causing it to start emitting a little bit of light already. The evolution of such a star and the planetary system can take many millions of years. Here, we can see the entire accretion disk, which contains all the materials like dust, small rocks, gas, and ice that the star will use to grow, but also from which planets may form. The physics of such a region is very well studied and characterized by their temperature and density, which are the two things that will impact the evolution the most. We've cut the disk into two parts and sliced it open so that we can show you the distribution of the densities and temperature. This half of the disk shows you the densities and is colored accordingly. Orange represents the lowest densities, while purple represents the highest densities. Knowing that, it's easy to see that the inner part of the disk is far denser than the outer parts. This high-density area surrounds what is called the midplane, or forms what we call the midplane, which is where we expect to find any planets that could be forming. The high density also allows for chemical reactions which are very important for the formation of larger, more complex molecules, which could even lead to the development of life. It's in the densest parts that the components of the disk can stick together until they become large enough to form what we call planets. These can either be gaseous, like Jupiter and Saturn, seen here in the back, or rockier planets like Earth and Mars, an example shown in the front, depending on the environment in which they form. We colored this side of the disk to show you how the temperature changes within it. Temperature is extremely important to consider as it strongly influences many aspects of how the system will evolve. In the center of the disk, we find this blue color, which represents the coldest temperatures. It is these cold temperatures that allows molecules to stick to little dust grains, forming ice layers and growing the size of the grain. These grains eventually can form planets, but they also allow for molecules to come close enough to each other in order to then react and form complex molecules. We often take these for granted, but we have to understand where they come from. As you leave the cold central region where the temperature is very cold, and go further up, you reach higher temperatures, this purple region here. The warmer temperatures can release the ices from the dust grains and some of the molecules on them as well into the surrounding area by the protostar. The release of these molecules increases their energy and allows for different types of reactions to occur that could not occur in the cold, dense part of the disk. So this is a very simple overview of what young solar systems, temperatures, and densities look like. To learn more about the light emitted by the protostar as well as the disk, stay tuned for the next video, and follow the Astro-Chemical Origins Facebook page linked in the description.
The journey of light begins. Our central star and the accretion disk that surrounds it emit particles of light, or photons, at different temperatures and different energies. As we travel through the different sections of the accretion disk together, we will see the temperature decrease and the photons become less energetic. Let's discover this together. Here is our protostar. It is our main heating source of the system. It has a surface temperature that is about 3/4 of that of our Sun, and it also has a magnetic field that interacts with the surface to produce hot temperature hotspots. From here, we see X-rays emitted, and these are the most energetic photons that we see in the entire system. Next, we have the inner disk, which surrounds the protostar. The temperature here is a little bit colder, and so the photons emitted are less energetic. They are in the optical regime, which is also known as the visible light range, because these are the photons that your eyes can see. Let's now focus on the external layers of the disk. We call this the photo-dominated region, or PDR. This region is exposed to energetic particles that are from the surroundings of the system. Species such as carbon and oxygen are ionized here, and these emit emission that is in the far infrared. Next, we visit the outer disk. In these inner layers that are closer to the protostar, the dust grains absorb the more energetic photons and emit less energetic photons in the far and near infrared. Further from the protostar, the temperature becomes very cold, and we have low energy millimeter and submillimeter emission. In this region, interstellar organic molecules like methanol are found. As we have seen, the different regions of the accretion disk contain different atoms and molecules that emit photons of different energies at different temperatures. These can be detected by different telescopes. For example, in astrochemistry, we use radio telescopes to detect the emission in the submillimeter and millimeter regime from organic molecules.
So this is the radio telescope. In our case, the main dish of the telescope has the diameter of 12 meters, and we can see here called main reflector 1. The reason is that depending on the energy of the incoming photon, we need a certain minimum diameter to detect them properly. Intuitively, the higher the energy of the photon, the less area we need to get a good enough signal, and this depends on the original energy of the photon. The main dish collects the photons. To focus the incoming light better, we need a smaller curved dish called subreflector in 2 here that reflects this radiation to the receiver where the image is collected. The idea behind this is that we need a certain focal length to focus the image, and for this type of telescopes, we mean that the focus could be outside the telescope itself. So we make up for this missing focal length with the distance between the main dish and the subreflector.
If we want to detect sources in different parts of the sky, we need a rotational structure to hold the antenna. This is made of 2 parts, a 360 degrees rotational structure and the dish support that can change its inclination, as you see in number 3. Once the data has been collected by the antenna and the beam reached the receiver, amplification processes and filtering can be applied. Ultimately, the data can be used to analyze properties of the source like the molecules characterizing and their chemical processes in number 4. Now let's see these molecules in detail.
But what do we see with a telescope? We have light coming from a star, going through an object, for instance a cloud, and then being detected in the telescope on Earth. This cloud is made of several types of atoms and molecules which interact in different manners with light. For instance, water molecule is a molecule that is found every part on Earth and also in space. When water is in the gas phase, it rotates and vibrates when it interacts with light. Here we have the rotation and 3 modes of vibration: symmetric stretching, asymmetric stretching, and bending. However, since the space is a very cold environment, we find water in the forms of ice. And this ice is amorphous, which means the organization of water molecules is not regular, it's completely random.
Building on the astronomical observation, we can build chemical models that can help us better understand the chemistry of the interstellar medium. As Emilia said, the water molecule is one of the most abundant molecules in the interstellar medium, and due to the cold temperature, this molecule is found in the solid state, so in its icy form. Here we build amorphous ice surface that, as you can see, has peaks and valleys in the surface, and amorphous means that the organization of the water molecules do not have a special ordering. The building block of this model is the water molecule here. The water molecule is composed by 1 oxygen atom, this one, and 2 hydrogen atoms. But we can not only study the composition of our model, but we can also zoom in and study the surroundings of one water molecule, looking at how many hydrogen bonds it does, and so we can take out structural data from this analysis. But these models are not just meant for structural analysis, but we can also study chemical reactions on the surface of them. So here we put a nitrogen molecule, which is one of the most abundant molecule in the ISM also, and it is mostly formed on the surface of these ices. So to cap it off, these models are really important to study the chemistry of the interstellar medium on the surface of interstellar grains in molecular clouds.
Some places in space, like molecular clouds, are very cold, relatively dense, and protected from the radiation of stars. In these places, molecules can form what we call icy mantles in the surface of tiny and solid small grains. And to understand this phenomena and have more information that can help us to understand what is happening and the telescopes observe, we can simulate these interstellar ices and study them in the laboratory. Here we can see an instrument that is used to replicate interstellar ices. So, for example, we can inject water into this chamber, the water will enter the chamber and then collide with a part of the instrument that is called cold finger. And why cold finger? Well, first is the size of my fingertip, and second, this surface is kept at a really low temperature, as low as 10 Kelvin, and this is just like as low as the temperature that we can find interstellar ices in space, like in molecular clouds. And using this device, we can understand more the properties of interstellar ices and study them.
In this video, we can see the blue particles fall on the surface. They represent the way in which small particles or molecules are approaching the cold surface. They will then accumulate along with nearby particles due to the interaction between them, gradually grow and stick on the surface. This might be a possible explanation of how the chemicals become enriched on the gray surface.
Hello from ACO!
Hello from ACO!